Welcome to Unit 2 of Structural Dynamics and Earthquake Engineering. In this unit, we will begin solving equations of motion for the simplest case, which is the free vibration case. So we will first look at undamped free vibration, then we'll add damping to the system and analyze what happens, and then finally we'll look at a specific type of damping, which is damping due to friction, which slightly changes the equations. Let's start with undamped free vibrations, and let's define what we really mean by free vibration. So the system we'll consider for this lecture is the simple spring mass system that you see here. And if you recall from our previous unit, the equation of motion for such a system is the following. Note that this is still generalizable to any undamped linear equation of motion, right? We can simply replace k and m with any other set of constants, and we can replace u and u double dot with theta or any other degree of freedom variable. Now, to get a specific solution to an equation of motion, we're going to need initial conditions, or ICs. These are an initial displacement, which we'll label as u of 0, and an initial velocity, which we'll label u dot of 0. Without initial conditions, we can only hope to have a general solution. But with these initial conditions, we can actually solve for a specific solution to the equation of motion. Now, the conditions for free vibration are two. The first is that the force on the system has to be 0. Okay, that's what it means for the system to be in free vibration. It is unforced. And therefore, in order for it to have any motion at all, the second condition is that at least one of the initial conditions has to be non-zero. So the simplest case would be we displace the mass by an initial amount and we let it go and let it vibrate. Or we could apply an initial velocity to the mass and let the system vibrate, or we could do both. So the final equation of motion that we will be solving is Ku plus Mu double dot equal to 0 with some known initial conditions. So as is the usual case with differential equations, we'll begin by guessing a trial solution. So our guess solution will be u equal to e to the st, and the corresponding derivatives of it are the ones you see here. So all we need to do is simply substitute those in to the equation of motion to get the following. And if you notice, the exponential terms simply can be divided out. So we're left with a pretty simple equation in terms of s squared, which we can solve. And so we have plus or minus because we're taking the square root, and we also have an I because the square root is of a negative quantity. So we have potentially two possible options for S. Before we set up the general solution though, let's redefine the value of square root k over m as the natural frequency, which we'll call omega n. So this is a very important value that's going to define the rate of oscillations of our system. Keep in mind that k and m are still generic values, so they could change depending on what our equation of motion corresponds to. K is simply the term in front of the displacement term, and m is the term in front of the acceleration term. So with that in mind, we can define two possible values for S. S1 will be equal to plus I omega n, and S2 will be equal to negative I omega n. And our general solution is simply going to be the linear combination of all possible solutions. So we'll say that the general solution for u of t is some constant a times our first possible solution plus some other constant b times our second possible solution. Since this solution is actually pretty hard to visualize, given that it has an imaginary component to it, we can express it in a more intuitive way by taking advantage of Euler's formula. This formula provides a connection between complex exponentials and sinusoidal functions, as you see here. So e to the I t is equal to cosine t plus I times sine t. Therefore, e to the negative I t will be equal to cosine of t minus I sine of t. So using these two formulas, we can rewrite our general solution as follows. Now we start to see why omega n corresponds to a frequency, because it is one of the terms inside of the sinusoidal functions. We can simplify this a bit further by grouping together the cosine and sine terms, like so. And then finally, we know that a and b are just generic constants, so we can collapse them together. And in fact, there's nothing that says that a and b can't be also imaginary numbers, so we can also collapse I in with them. So we can treat this term as a constant, and we can treat this entire term, including the I, as a constant as well. So that leaves us with simply a combination of cosine and sine functions. Notice that we could have guessed cosine and sine as potential solutions to the equation of motion, and that would have worked too, but I find it easier to use exponentials to solve, because you essentially can always start with the same trial solution. And then you can use Euler's formula at the end to convert to sinusoidal functions. All right, so that's our general solution, and we can't go any further until we consider the initial conditions. So let's actually do that and plug in our initial conditions to the general solution. So we'll start with the displacement initial condition, which is u of 0. So that means we essentially plug in t equal to 0 to our general solution. And we know that cosine of 0 is 1 and sine of 0 is 0. Therefore, c, the term c, is simply equal to our initial displacement. We do the same thing for the derivative of the general solution. So we need to first solve for u dot of t by simply taking the derivative of our general solution. Notice that we get a omega n term on the outside. And then now we can plug in t equal to 0. The same simplification as before now gives us the sine term equal to 0, and so we get d omega n equal to u dot of 0. Sorry, forgot the dot. And therefore we get d equal to the initial velocity over the natural frequency of the system. So our specific solution looks like so. So armed with this solution, we can immediately find the response of any general free vibration system with specified initial conditions, right? We don't need to solve the equation of motion every time, right? We simply plug in the respective values. So this is a good equation to have on hand for free vibration problems. So now let's plot u of t and see what we can learn from it. So this is just a generic plot for some initial displacement and initial velocity. And notice that the response is simply a sinusoidal function, which has a constant amplitude. Amplitude we define as the distance from the 0 point to the peak of that sinusoidal function. It may not be intuitive, but a sum of cosine and sine results in another sinusoidal function. So what is happening? Whenever this curve crosses 0, as in this case A, our single degree of freedom system, which we're using a frame in this case, is simply at the equilibrium position. We're plotting displacement after all, so displacement is 0. When it peaks, it means that the system is at the maximum point of displacement. In other words, it's pushed all the way out to one side. At that point, the system stops accelerating and the stiffness pushes it back, or brings it back to the equilibrium position, again C, which then it overshoots and goes to the maximum displacement on the other side, which is D, and the process continues over and over. Okay, so it's similar to a pendulum, just going back and forth. What else do we notice? A period of oscillation, which is the time it takes for the system to complete one full oscillation or one full cycle, is called Tn and is inversely proportional to that natural frequency variable that we defined earlier. So it is simply 2 pi over the natural frequency. So as the natural frequency goes up, that period is going to shrink. So the system is going to oscillate at a faster rate. The last thing to notice here is that if we change the initial displacement or change the initial velocity, which dictates the slope of that displacement, then our function is essentially going to shift. So if my initial displacement is 0, then I would get the same function but starting at a different point. There is a slightly different way to express this solution, which makes more sense in certain cases, which is the amplitude-phase representation. So instead of representing it as a sum of two sinusoids, we represent it as one sinusoid, sine, with a specific amplitude, which we defined before, and a certain phase shift. Recall that by changing the initial conditions, we introduce a shift in the response. We also would influence the amplitude as well. So amplitude and phase shift, or phase, are simply functions of the initial conditions and omega n. As shown here, you can imagine this relationship graphically. So if we have an axis for the cosine term, which is the y-axis, and we have an axis for the sine term, which is the x-axis, we can plot the corresponding amplitudes for each of those two sinusoids, which would be v0 over omega n, or this is the same as saying u dot 0 over omega n, and x0 or u of 0. So those are the amplitudes of each of the corresponding sine and cosine terms. The overall amplitude of the signal then is going to be the hypotenuse of that triangle, right, or the magnitude of that vector. right? So it is simply what you see here, a square root of the sum of those two terms squared. And the phase corresponding to those two choices of initial conditions is going to be the angle of that vector. And so that corresponds to inverse tangent of x0 over v0 over omega n. Right, again, note the equivalent variables here. So notice that when phi, the phase, is equal to 0, that means that the initial displacement is 0, and so the sinusoid is going to start at 0. On the converse case, if phi is equal to 90, the slope of the curve is going to be equal to 0, and the sinusoid is going to start at the peak. Okay, so this is a slightly better representation, in my opinion, to visualize exactly what the curve would look like. Lastly, we can also visualize the amplitude-phase relationships between derivatives of u to look at how the corresponding amplitudes and phases change as we go from displacement to velocity to acceleration. So let's go ahead and plot these side by side. So let's start with the displacement solution, and we'll just again draw a generic type of displacement curve here. This is going to have an amplitude A and a phase shift phi. Notice I measure my phase shift up to the point where the curve crosses 0 in a positive direction, right? Because that's where technically a pure sine wave would start. Right, now let's look at the solution when we take the derivative of it to get the velocity solution. Notice that we have now an omega n term on the outside, and our sine changed to a cosine term. But a cosine is nothing more than a sine shifted by 90 degrees, or pi over 2, so we can express this in terms of sine so that we can make a direct comparison. So we get a rational phase shift plus an additional pi over 2. So pi over 2 is 90 degrees, or a quarter of a cycle, so we can shift, so essentially we shift that signal by quarter of a cycle. So we have now the 0 point lining up with the peak of the displacement. And the 0 crossing on the displacement is going to line up with the peak of the velocity. And I've drawn this poorly, but the negative peak of the displacement should correspond to the negative 0 crossing of the velocity, and so on. And also, our amplitude is going to change, right? So this is going to be now equal to a times omega n. So that could grow or decrease depending on the value of omega n. And again, to be clear, this is phi, and this is an additional pi over 2 shift. And very similarly for the acceleration, we expect to see another shift by pi over 2. So we see that the result is now negative a times omega n squared. We're back to sine, but this is a negative sign, and again the same argument there. So negative sine is simply sine shifted by pi. So we rewrite this as a times omega n squared sine of original argument plus pi. Okay, and so now we shift by half a cycle. So wherever phi was, now we're going to shift by pi. And so our positive 0 crossing is there. Our peaks line up with the 0 crossings in the velocity, and so on. Okay, So this is just a visualization of what happens when we go from displacement to velocity to acceleration. Notice that the signal actually does shift. So this shows us that acceleration, velocity, and displacement peak at different times, right? They don't all peak at the same time. That makes sense, right? Because when the system, the mass, is at an extreme of vibration, that's when the displacement is maximum, but the mass actually stops at that point. So the velocity is zero. Conversely, when the displacement is zero, the mass is at the equilibrium position, it is actually at the maximum velocity. And the acceleration, which has an amplitude of a times omega n squared, is actually always opposite in sign to the displacement.